Hello. Today, we are focused on a critical question. Why is echo-cancellation an enabling technology for simultaneous bidirectional SBD SerDes? SBD promises to double bandwidth efficiency by sending the data in both directions on a single wire at the same time. While this double throughput per I/O, it creates a fundamental problem. The powerful local transmitter signal leaks directly into its own receiver. Even on clean, short-reach links, the near-end echo is typically 20 to 30 dB stronger than the attended far-end signal. Without cancellation, the receiver's front-end would saturate, and the desired signal would completely lost. The goal is to use an analog hybrid to suppress the bulk of the echo. Then use a digital adaptive filter to remove the residual. A practical target is to reduce the analog residual to less than 30% of the far-end signal's amplitude, allowing a small adaptive FIR filter to provide the final 10 to 15 dB of cancellation needed for clean signal. The first line of defense is the classic analog hybrid, a passive transformer or resistive bridge. Its function is to create an inverted copy of the local transmitted signal and separate direct at the receiver's input. This approach is broadband at no latency and typically provides the first 15 to 30 dB of echo cancellation before the signal reaches an ADC or data slicer. However, its performance is dedicated by impedance matching. Any mismatch in the line impedance, package parasitic, or pack capacitance will unbalance the hybrid and leave a frequency-dependent residual echo. The key to success is meticulous design. Use small, trainable termination network, roughly plus minus 10%. Ensure precise symmetry in the layout and return path. And verify cancellation now is deep and flat across the entire signal bandwidth. The primary goal is to preserve the ADC's dynamic range, so the digital backend isn't forced to recover a signal from a clip waveform. An alternative is the pure digital approach, common in DSL and copper Ethernet PHYs. Here, the ADC digitizes the entire composite signal, the weak far-end data, plus the stronger local echo. An additive FIR filter uses the non-local transmit signal to build a precise digital replica of the echo and separate it, sample by sample. So for short-reach SerDes, a 2 to 6 tap FIR filter is often sufficient. The build-up process is well defined, with far-end transmitter mute. A training pattern like a PRBS is used to adapt the filter coefficient via LMS or normal LMS algorithm. Once trained, the link switches to a decision direct mode with a low update rate to track slow environment drift. The major change, however, is ADC's dynamic range. This architecture places entire burden of handling the powerful echo on the ADC, which must digitize without saturating. In practice, some analog separation is almost always needed to keep the converter in its linear operation range. Alright, for demanding channels, the industry standard is the hybrid or combinational approach. This strategy leverages the strength of both domains. A robust analog hybrid provides 25 to 35 dB of initial cancellation, and a short, efficient adaptive FIR filter adds another 10 to 20 dB of precision cleanup. This combination reliably achieves the 35 to 50 dB of total cancellation required for an open healthy eye in a full duplex operation. The build-up sequence is systematic. Purify and trim the analog hybrid for deep now. Turn the digital FIR filter, and then enable the far end live traffic while a slow background adaptation loop tracks any drift. For robust operation, it's critical to monitor both the pre-ADC receiver to detect analog drift and post-equalizer eye and error rate to catch any divergence in the digital adaptation. An elegant, though less common technique is dynamic reference switching. Instead of subtracting an analog current over voltage, this method targets the receiver decision schedule in sync with the local transmitted bits. This effectively subtracts the local signal at the precise moment of data sampling, while the analog overhead is low. This approach is difficult to implement at multi-gigahertz speeds. It requires distributing a reference signal at a full data rate with extreme tight skew and jitter control. Even minor phase errors between the data and reference can manifest an intersymbol interference ISI, degrading the performance. Active analog cancellation techniques, such as a replica driver and switch capacitor hybrid, offers deep echo-cancellation without magnetic components. This circuit creates the anti-echo signal using a scale replica of the main transmitter driver and actively separates the receiver. The primary change is that the replica driver does not experience the same capacitor as the main driver, causing its high-frequency behavior to diverge. Achieving a deep now requires intensive calibration to trim both the amplitude and phase of the replica signal to precisely match the true echo path. This typically involves 5 to 6 bits of amplitude trim, fine-grained delay adjustment. For example, 1 of 16th unit interval, and a two-dimensional calibration sweep during link initialization. For the modern short-reach SBD links often favor the resistive-gm hybrid, the form of split termination subtractor. This circuit sends the transmit current via a small series resistor and the output driver. The voltages on either side of the resistor are fed to a pair of matched transconductors GM stage, whose output current are combined to cancel the local transmit signal while passing the far-end signal. Its main advantage is that it operates in continuous time, eliminating the need for sampling clock and simplifying phase alignment. The trade-offs are classic analog changes, achieving tight gain matching across process, voltage, and temperature PVT variations, maintaining linearity in the GM path, and accepting a small loss of a transmitter voltage headroom across the sense resistor. A common replica for 20 to 30 plus gigabit per second links is to pair a resistive GM hybrid with a short 2 to 4 digital FIR filter to clean up any remaining frequency selective residual. Here are a summary images showing you why echo cancellation in SBD SerDes is a must. The core concept behind successful SBD is straightforward. Use the amplifier side to cancel the overwhelming echo from your own transmitter. then apply a small efficient adaptive digital filter to remove what remains. This two-stage approach is what makes it possible to double the bandwidth per I/O by selecting the right hybrid architecture for the channel, training the adaptive elements intelligently, and implementing the link to monitor for drift. You can achieve full duplex communication on a single lane with a low latency, power efficiency, and high I/O density that modern chiplet-based and high-performance computing system demand. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and place your comments down below. Lastly, please share the video with the people who may be benefiting from it.